Hey, good morning.
Good morning, everybody.
Hello, everyone. Turn on my volume a little bit. Did you hear me?
Good morning, Bobby. Loud and clear.
Oh, great. Hi, everyone. It's good to see you in the breakfast. And I think I've met also have other people coming into the breakfast as well. It's good to see you all. And if I didn't see you in the OFC, hopefully we'll be able to see you on some other chances. So I think one of the big news in previous couple of days, besides the OFC, there's lots of new optical comes out. Besides the CPO becomes a big news. There are many other 200Gs modules becomes like a big major things that peoples are pushing, and start talking about 400Gs in reveals in the surface. One of the big things that will affect us a lot is UA-Link finally have the 1.1.0 spec ready, and it's ready to download. So what I will do is I will upload the spec into our Google Drive and share with people in here. If you don't want to download from the UA-Link spec, you'll be able to view it from our Google Drive, and also other I think press release materials. There are a couple of them, smaller white papers and a PowerPoint. They're all public available now, and so I'll put it into our Google Drive, and you'll be able to read it, and hopefully we can have some deeper discussion in the next couple of weeks. That is what I will do. Anyone like to share some things about the OFC this year? Well, that might, maybe my audio is bad, so I couldn't hear everyone clearly. So,
I heard you.
oh, okay, great, thanks, Jeff. So I mean, if no one want to share anything about the OFCs, I think we can move on to the next topic, which is Jeff, do you like to share the some of your work?
Yeah, sure. Did that work? Are you seeing something?
Yes, it pops on now. Thank you.
Okay. So I was talking to Bobby last week or whenever that was, and we were talking about, maybe a presentation and what we could share. As part of the OIF, I presented this. This is Optical Interconnect for AI. It was one of the panels, show floor 15 or whatever it was. And so we had a couple of speakers there. Ashkan from NVIDIA was one, and I was one. And so anyway, this is kind of a summary of what we presented. So and I thought I would just go over this quickly, and then if there's any questions or comments, I'd be happy to answer those. But anyway, the key message here is that AI, we really need to do something, and for these larger training clusters, we're going to need copper for shorter reaches, optics for the increased connectivity over long distance. The links have to be energy efficient, low latency, and high reliability, and they have to support a variety of protocols. So that's sort of like the overall message of the presentation. I think you've seen this slide before, but it just details. This was originally created by Microsoft, but it identifies the 5 different links that are used in the AI compute. And what I've circled in red here are the links that are typically copper, and the ones in blue, which are typically optical. And that's where things are today. And if we look to the future, what we expect to see is that we expect to see copper optics come into these links 1, 2, 3. In fact, primarily the first place it'll show up is in link 3, link type 3. But that's where we expect that to occur. In terms of the requirements, I think you've all seen this as well before, but these are some of the requirements, again, by the hyperscalers. They all contributed information to it. So this is sort of a high level. Certainly some links could be have worse numbers than shown in this table, but this kind of gives you the characteristics that would be for links 1, 2, and 3 in the orange, and then green would be links 4 and 5. And if you meet these, then your links should be able to work in any one of those applications. One of the things I'd mentioned at the bottom that doesn't get talked about enough is reliability, which is divided in 2 categories, both link errors and hardware failures. And both aspects of reliability are really important for this AI compute in the local cluster connections, local HCPU connections. So this is a slide that we had. This shows the NVIDIA system with many differential pairs, 5,000 differential pairs running through the backplane. And not that you would do this, but if you were to replace all those with optics and you used 800G fully retimed modules, it would add about 20 kilowatts of power to the rack. And the reliability failure rate would increase by about 100,000 fit. So that's clearly not practical to replace these AI compute links. And the question is, we really need a better way to do that. And how might we do that? And again, the goal is in this rack, everything's close enough so you can use copper. The question would be, could you figure out a way to connect more GPUs and maybe go across racks or something?
So
Jeff,
Jeff, I have a quick thumb question.
Yeah.
What is FIT? FIT?
Stands for failures in time. It's a standard measurement for reliability for modules. And there's 2 kinds. There's the 3 kinds. There's what you call infant mortality. There's what you call random fit, and then there's what you call wear out. And in these things, mostly we're talking about random fit and infant failures. And it
Thank you.
represents, one fit represents one failure in 10 to the 9th hours.
10 to the 9th hour. Okay. Thank you.
It's a standard measure. You find it on most data sheets. People who sell things will have fits. If you look at like a best-in-class optical module today, you'll find something over 50 fit for the module.
Yeah, but I struggle with this. I mean, so Intel talks about 1/10 of a fit for theirs, right? And I don't know, my common sense, my logic, if you're at that level, I don't see why there's a problem. So there's something missing about this. It's not about the fit, it's about the distribution or something. It's not the
Well,
fit.
I guess I don't understand. What's the question?
The question is broader than what you're presenting here. I'm just struggling with understanding,
Well,
looking at a fit and understanding how that or why that is important. It's not the fit, it's the distribution.
yeah, let me explain it. So it best I understand it. So if you've seen some of those slides that Meta and others have presented, they show what happens with an AI cluster if there is a failure, how the whole cluster stops. In these local clusters, when one thing writes to memory, none of the others can access that memory until that's complete, and they all kind of work in lockstep. So what happens if you have an error in one of them, it stops the whole local cluster. You spend a lot of money for one of these things, so when it's interrupted, even if it's not a hardware failure, even if it's just a bit error, it causes the thing to hiccup. They routinely do save points, so they save all the parameters, set that off to disk someplace, and then if they do have a serious failure, they can replace stuff, and then they restart from the last save point and continue forward. Meta at OC also presented again their famous slide showing one of the training cluster runs that goes over like I don't know a period of months or so, and you can see just multiple interruptions. Like once every couple days, there's a failure, and they have to go and fix something and restart the training cluster. And because there's so much investment in these things, they really try to avoid downtime, because then it's all this money just sitting idle.
Now, Jeff, you also should point out your 100,000 fit here is because you're adding up maybe 1,000 transceivers. So you're adding individual fit up, right?
Yeah.
So that's why the number is so big. Yeah.
Yeah, and that's right, and that's the point, is because this is a system, and and you can't just have part. It's not like a regular Ethernet switch where something fails and you just label the port down and most of the data center keeps running. That's not the case in these local clusters of GPUs. When something fails, the whole rack is down. It's not like you can keep on running.
So where does this
Right.
where does this number come from? Where's the estimate come? Where does this estimate come from?
Well, so you could do it yourself. There's about 5,000 differential pairs. And those differential pairs would be, you divide that by, if it was 800G module and it was 200G, that would be, I don't know, is that 4 channels per module? So you could divide the number of differential pairs by the appropriate scaling factor to get it in terms of modules, and then take the modules and assume maybe something like 50 fit per module, and that's
Gotcha.
what you got.
Okay, gotcha. Thank you.
Mm-hmm. So then I think you guys have seen this before. I'm sure you've seen that there's pluggable modules on board and co-package, and pluggable modules. The biggest thing about them is they're replaceable. So if something fails, you can replace them. There are 3 types of architectures. Sort of ones without DSPs and non-retimed ones. There's ones that have TX retimed, and then there's fully retimed. There's also the possibility of doing an onboard module, which certainly increases the density. You get a shorter electrical channel, and the replacement though requires the whole card to be removed. And then there's co-packaged, which gives you the highest density, the shortest electrical channel. But if it fails, pretty much you'd have to repair the ASIC package, which isn't going to happen. The other thing is that the way that the system is put together, what kind of optical interfaces or electromanagement, that has to be configured during the ASIC packaging stage, which is something that they don't necessarily like. But these are the options that people have to do this. Now, if we take a look at the types of interfaces on here, I just show everything from an active copper cable, which NVIDIA is using in their NVL72, right, all the way down through some future version, which is a slow wide interface with chiplets. so you have this range of things to do that you can use. This particular slide I didn't present at OIF. This is presented at the Ethernet Alliance and the TEF. So I put 3 slides in just to show that. Now, one of the things I mentioned was about the shorter electrical channel being important. So I thought this is an interesting chart. On the left, you see electrical channel insertion loss here on one side. And then this side, you see the energy utilization in picojoules per bit. And I show different lines for fully retimed, TX retimed, non-retimed. And then this is sort of a PCIe interface. One of the reasons this one is lower than say the non-retimed Ethernet is because it has a light effect. So bit errors it's not as resilient to bit errors. And so it's going to be lower. There's sort of this dotted line, which is a plug and play boundary. If you're to the left of this boundary, sort of in the green region, you have lots of margin and everything works pretty well, pretty nicely. If you're to the right of this, you probably had to do some system tuning. Maybe you had to use a more powerful SerDes. Maybe you had to carefully train, each of the different ports you have. But that's kind of the way the thing works. Not that things to the right of the line in the orange and red aren't possible, but they certainly have less margin. And one of the things that's really important in these AI clusters is lots of margin. They just don't want to have any, flaps or, bit errors or hardware failures. So they really would like to have lots of margin to make sure things work. In the right graph is the relative latency. So you can see the different interfaces from non-retimed, TX retimed, fully retimed, and then this is the PC fully retimed but PCE-like lengths, which have much lower latency in them. So I think this is the key thing, is that if the shorter the electrical channel, the more robust link you'll have, and you'll be able to get the energy efficiency. Then the next slide is just a representation of some of the target parameters that we got from the hyperscalers. So this green region represents the hyperscaler target region, where we have an energy utilization less than 5 picojoules per bit and a bandwidth edge density of 2 to 4 terabits per millimeter. That's what this region represents. What I show here in this color here is the OCP modules, from fully retimed all the way down to passive. Then this column would be the copper cables, passive copper cables. So this green dot represents about where the NVIDIA system lies. And then I just should say the way the bandwidth density is calculated is we take the ASIC, which has say 7.2C SerDes on it, and we take the number of OCP modules, say for instance in this case that you'd have to line up to service that, and it's the minimum width of these modules which limits the bandwidth edge density. In this case, this would be an example of a chiplet, that kind of would match it. So the minimum width of this system would be this chiplet width. So that kind of gives you the idea of how we calculate the bandwidth density. And I should mention that the energy utilization is just of the engine, not including the SerDes. So that's how this particular graph has been put together.
Jeff, question. The lower left-hand corner, the CPO,
Mm-hmm.
7.2 millimeter. Is that on the package, 7.2 millimeter?
No, that's the width of the chiplet.
The width of the chiplet. Oh, so you are saying that to support the pluggable right to the left of the CPO, the chiplet need to be 22.6 millimeter? That doesn't make
No,
sense.
I'm sorry. So these would be OCP modules.
Right. So
Right.
that will be at the edge of the motherboard, right?
At the motherboard, right. And so what we're showing here is that for 7.2, you'd actually need 5 of these. They're only drawn in 4, but each one of these is 22. So you need 5 times 22.
Oh,
But you see this little white area here? That's the
Yep.
width of the SerDes block for 7.2 T bandwidth.
Yeah, so it's normalized to 7.2 T. Okay, got it.
Yeah, and where that 7.2 came up with, that's the data rate in the NVL72 on the ASIC. The capacity of the SerDes on the NVL72, so that's where it came from.
Yeah, but when the CPO fan out from the package, eventually it still need to hit the edge of the tray or the board.
Well,
Oh,
but then it
oh.
would be fiber, right?
But that will be fiber, correct.
Mhm.
And the module for the fiber should And if it is linear optics, I'm just thinking out loud, sorry. If it is linear optics, then the module can be a lot smaller than the OSFP.
Yeah, that's right. OSP has a lot of housing around it and other things, right? Exactly.
Okay, thank you.
Okay, so then what I showed was where we think the next generation could be. So in this area here, I show the high density connector that project that the OF's working on. We don't know exactly where it'll end up, but this would be my guess. Somewhere in this range is where it would lie. And then this is where I think if you look forward to what people are announcing for co-packaging, probably somewhere in this range is where co-packaging is. So this green region is a tough target, but it kind of gives you a variation of where we are today and where we think we could go with some of these approaches. Okay, and then I think we had a little discussion on 400G. So I just put this slide in. This is again from the EA. So in the top one, this says let's assume we use the best modulation electrically, then the best modulation optically, and then the best electrically again on the far end. So this green block would have to do the conversion from, if say this is PAM6 and this is PAM4, then this block would have to do the conversion from PAM6 to PAM4 and back again. And that wouldn't be the most energy efficient scheme. In two, you could say, well, maybe I want to try the best optical modulation. So use that over here and here and here. So you wouldn't have to do any conversion. And then you'd have some kind of linear element here for the optics. But the problem here is that the copper really can't sustain that bandwidth at this point, as far as I know. So that may not be the the best way, and probably results in some compromises. But what's shown in number 3, probably maybe the best path forward. This is where you use a slow wide interface between the ASIC and the optics. And then you put the SerDes in the optics and then use the best optical modulation. If this were going to be a copper link, it'd be the same scheme, but then this SerDes would generate the modulation for the best electrical link. And this way, you would have the best, you'd probably have the best, way to do the interconnect. So anyway, those are the options. I don't know what the answer will be, but that was one of the slides we presented. And anyway, this was just a slide that shows what projects we're working on and 448 webinar, and then that's the summary. So I don't know if that helped, Bobby, but that's what I had.
Oh, it definitely helped. I think this the picture that you presented on, I think the previous one, that would be a next generation high density connector, and also the co-packaging one. That would be one of the base things that we can put it into our discussion for the UA link, because what I think UA link at the beginning, it kind of clearly defined how many how wide the bandwidth supposed to be for the GPU or the accelerator, and it defined like a 1028 ASICs needs to be connecting together. So that is that is kind of a predefined target, and it certainly does not limit it into the has to be achieved 1028, because you could have different levels of a hierarchy. For example, in a rack, you can be much shorter and higher density, and then you have another levels to going into a different rack. And so it would be a very good numbers for us to going into a different approach, because what I'm thinking on is a lot of us that will probably stay in the pluggable range, pluggable for the UA link solutions at in a short time, and in the you would probably have a statements for that. Then we can working on how would be how would be the main advantage of staying in the pluggable way. And you did point it out many advantage for that. For example, the fit rate could be a big problem, and then how to be easily as easily access and replace the component would be a key advantage for fixing this problem. But for some of our members, they are working on something like near packaging optics or a CPO. They would clearly have a good advantage on, for example, the energy utilization, the shore density that would help. And so for our white paper, we can have many different perspective to staying each company's advantage, and that would help the OCP greater community to pick the technology to for the future I think the future rack or an OCP AI system to choosing from. And besides UA Link, I think I'll also I think we should also read the OCP recently just announced that the AI server system. I think they announced that they have the huge paper for that as well. I'll try to sum up with some key spec for us to looking at, and perhaps we can work together and to come up with something.
Sorry, this is Michael Liu from Intel Foundry. Thanks, Jeff, for the great presentation. Just a couple of quick questions for you, Jeff, if I may. Hello, can you hear me?
I hear you. Can you hear me?
Yes, yes. Okay, first question, can we get a copy of your deck after this?
It's up on the Google Drive.
Okay, understood. Second question, on the left-hand portion of your slide here on the screen, have you considered a CPC, co-packaged copper cable connection or connectivity?
In this slide, I don't have it. In the TF slide, I did have it. So in the TF slide set I did, it's in there. So there's different versions of it. In particular, I contrasted some of the, I can't remember which company it was Amphenol or something, versus Samtec. The Samtec was 0.5 pitch. It was much denser, right?
Understood. So any reference or exposure to Sumitomo's design rules or reference points?
I mean, I could, in another one, I could assemble a few of those slides to show what I had done there. I actually compared copper versus various optical technologies for the optical engine, for the modulators, and how they compared size-wise.
Good, good. I will look forward to it. Thank you.
I do have one slide I can just share briefly. We're talking about the reliability. If I can figure out how to make this thing stop sharing. Stop share, there it goes. Let me just share. This is a slide that Meta had presented. Can you see that okay?
Yes.
So this is just their one slide they had on hardware reliability impact. They showed this at OFC a couple times as well again. But this shows progress through a training run, and these orange lines represent failures of some sort where they had to do a restart. This shows an example of a restart where progress stops, they get things replaced, and then they restart again. And they talk about the, this is I think this was with, yeah, I think reduced bandwidth or BER issues that occur, and they show the performance degradation. Of course, that slows down the entire cluster. So just as some reference material for where they were thinking.
Well, they can recover the job in less than 5 minutes. That's that's amazing.
Which is a key thing, that's another key thing about the choice between, say, LPO and other things, in that when something goes down, in order to do that quickly, they need to know what to replace. And so they really want robust diagnostics to find where the problem is, so they can get it fixed quickly and get it back up and running. And that's one of the things, LPO doesn't, traditional LPO modules don't provide that level of diagnostic capability.
True. And I thank you, Jeff, once again. So I think if you can share the CPC slide for next time, that would be wonderful. And I think it's about time for our schedule time slot that we ends up at 11. If no more questions to Jeff, I think we can conclude the meeting this week. All right. Thank you, everyone. I'll share the Jeff slides in the meeting in another email. Thank you, and we'll see you next week.
Thank you.
Thank you.
All right.
Bye-bye.
Thanks.